let's get lecture started today. So let's see what announcements we have. I guess one thing I do want to share with everyone is, in case you missed out, in Brightspace, I do my best to try at the start of every week to do a weekly summary. So on the side column, there's weekly summaries, which are things I type myself with a lot of copy and paste help. So it kind of describes the topics we'll cover in lecture. So generally it's the topics from the table of contents of each lecture set. These are the learning objectives tied to course outcomes, and then the reading from the textbook that corresponds to what we cover, the lecture set we're working over, reminder about homework, and then what assessment is going to happen at the end of the week. So if you're someone who's feels like you're having trouble keeping track of the high level picture of where the course is going, I recommend you check out the weekly summaries. Right. It's a nice resource. I try to do it for people who need that sort of high level view of where the course is going. Announcements. So we are about at the halfway point of the course. Hard to believe. So at least content wise and material wise. So, this is where we need to start, formulating questions, gear up and start compartmentalizing and accessing information to gear up for the final. Ria, can we expect the exam 1 grade before exam 2? Yes. If favor is on our side, we should have all of exam 1 graded by Monday of next week. I plan to start grading exam 1 today. Right now, haven't started any of the grading, so none of the exams are graded. Is the final exam cumulative? Yes, the final exam is cumulative. That's why it's worth 4. Get all the crying out of the way before exam 2. Have mercy on our grades. I mean, I'm expecting a healthy curve. Put L in the chat if you thought the exam was too long. I think that's the number one complaint about the exam, or at least too long for the time given. Oh look, suddenly we have a bunch of agreement from everyone, and people think democracy is dead. A 4 problem exam would have been amazing. Yeah, I mean, I'll keep that in mind, but I just think we asked too many parts, especially for the MOSFET questions. The MOSFET questions, I think, just drug on a little too much, especially that first one. You could have lived without problem 4. Problem 4 was a series RLC circuit, if I remember right. Well, that one's tied to a learning objective, so, or not quite. Let me briefly look at my cheat sheet and see what it says. It was a series parallel CLR circuit. I felt like that was within the realms of capability. Did anyone feel like the exam problems were just plain old unfair, like they were of a difficulty that you could just not have anticipated? I mean, I think, Boyu and I did a good job to make sure that the questions were, of a reasonable difficulty. They were maybe one step beyond lecture, but not quite as bad as some of the lecture. Yeah. I mean, if you have, a couple people had some feedback on what to do differently with exams and, had some maturely put, criticism of how the exam was conducted. If you are someone who feels like, you can articulate it well, what was wrong without being, bashing or without, completely unworkable ideas, feel free to send emails. Those are things that I will share with the teaching staff. Yeah. I guess one thing to note is that with series of parallel circuits, or with RLC circuits that aren't purely in series or parallel, you will get like a form of the characteristic polynomial that matches one of the series or parallel cases. Like it should match the series or parallel case. You just have to work a little harder to derive what it is exactly. And like the natural frequency will still be 1 over square root LC and things like that. So that's never been stated in the class before, but if you've played around with these problems, like, or experienced it firsthand on the exam, you should have hopefully been able to figure that out. So that's that. Homework 3 is due today. This is where I'll ask you again to be mature. Is anyone going to have problems making today's deadline? Speak up if you are. I see 1, 2, 3, 4, 5 and 4.5, 5.5, 6, 7, 8, 9, halfway done. Okay. All right. Enough of that. What day would you like the homework to be due? Obviously, I know some of you would say never, but like what's pushing the deadline back to tomorrow? Tomorrow being Wednesday. Same as quiz. No, I'm not going to push it back till Friday. I mean, I might do Wednesday, Thursday if you were desperate. Tomorrow, noon or midnight. Tomorrow midnight. Because we're not even started with the exam grading, so like I feel like I think Wednesday is reasonable. I will put out an announcement that I'm pushing the deadline back one day. Don't say I never did anything for you. It's nice being the instructor. I can make these decisions unilaterally. All right. Yeah, I feel like that's fair. Any other administrative questions with this course? We spent about 10 minutes on it. Oh, okay. Yeah. I'll be accountable and say, hey, we do not, the teaching staff does not have all of it graded. Point your anger at me. If you're one of the people who doesn't have their homework 2 graded, I apologize. I will be on the TA's case a little bit more to get homework graded in a more timely fashion. Alice has a question. Does quiz 3 cover last week's content? Quiz 3 will be a mix of convolution content, lecture set 3, and there will be a little bit about whatever we cover on Laplace transforms up until Thursday. So, in fact, I will even be generous and tell you that there are 2 questions on convolution, our lecture set 3 material to be more precise, and there's 1 question on lecture set 4 material. So pay attention. Any other administrative type questions? I feel like the group here that's in the lecture, synchronously, I feel like you all had an advantage on the exam. You may not feel like it, but like compared to some of the complaints I had with the people who weren't taking the exam or who weren't following along synchronously, I feel like the synchronous group tend to do a little better. In the same vein, I also feel like the people who are following along and listening to my lectures live tended to know how to turn in the exam better than the people who were not following along live or who had not caught up on lectures to know that I said, hey, there's a grace period that happens once the counter reaches 0. So give us a bigger curve? No. You guys just get to set the curve a little bit more directly. Nice try, AJ. All right. I think that does it. let's go ahead and start new content. Makes me excited whenever we have a new lecture set. So here's lecture set 4, Laplace Transforms, available through Brightspace. Act now. So this covers the Slavich and Turlip textbook, this textbook that hopefully you guys have been following along with whenever you can't understand what I'm saying or think I'm going too fast. You use the textbook. If you do have, honest feedback about what I'm saying, for a given lecture, do speak up. Like, if I'm going too fast, do let me know. If you want more examples, I talked about why I don't have more examples prepared. I think there's this misconception that I'm sitting on this Fort Knox worth vault of worked out problems, but the answer is no. Most of the problems you have are either from the textbook directly or I worked out myself. It's not like I have like, a list of handy convolution problems ready and solved that I can just throw up and work out with you. And those who want problems worked out live, that's going to be really hard just given the format of this class. So, man, I am listening to your feedback. It's just really hard to act on sometimes. Okay. Yeah, if you're having Brightspace problems, try a different browser or reload. Whoa, that's not right. What are we going to cover? So first we're going to start with, 3 topics covering the math. So an introduction to the Laplace transform, including how we work it into ordinary differential equations, and we'll develop what are called Laplace transform pairs, time domain function and the Laplace transform of that function, and see how you go from one to the other for various functional forms. Laplace transform properties will be most of tomorrow. And then the inverse Laplace transform will be on Wednesday. And that will cover some big things, including the convolution property, as well as duality, and then the rational function structure of the Laplace transform. So we'll get heavy into the math and possible cases of examples, and then some LTI system responses. Then we'll start applying it to circuits. So we'll talk about impedance and admittance in the case of the Laplace transform, initial conditions with Laplace transforms, and then we'll get a little bit into the sort of engineering mentality of how to work with Laplace transforms. So transfer functions, and then response decomposition, the different ways to break up, the response of a circuit into different components, usually a pair of components. So why learn Laplace transforms? You're going to learn that this is, hopefully you've seen that it's a pain to recalculate the particular solution to a circuit initial value problem for all inputs of interest. So the ODE method has its problems. Convolution with the impulse response allows us to find the solution for any input, but man, are the integrals burdensome, especially when you have to do integration by parts, as you're probably feeling heavily on this homework assignment. We want a tool that removes the calculus from view entirely and leaves just rational function arithmetic. So just, working with functions and doing arithmetic on them, called the Laplace transform. So the Laplace transform is built around complex exponentials, which is the fundamental part of our solutions. If complex, we mean both real and imaginary parts, or real and imaginary parts in isolation. That covers, the major cases for all of our ODE solutions. So we should anticipate that if we use complex exponentials and bake it into our Laplace transform method, whatever it may be, we're going to get all of our possible circuit responses, as well as, hopefully get the fastest linear circuit solution method out there. So we're still asking the same question. Given a circuit, which is a combination of resistors, capacitors, inductors, and if we're feeling cruel, dependent sources and transformers and op amps, what is the, output to a given input, which might be a step function, an impulse function, a ramp function, some combination of those, a sinusoid, an exponential decay, something like that, or an exponential decaying sinusoid from a previous circuit. So this will be the last time we revisit this problem. This is our third go around at it. but hopefully we'll see that the Laplace transform is king. This is one of the most important lecture sets of ECE 2002. Yeah. In the exam, you should have gotten the grace period where the clock read 0. You should still been able to edit your answer for 15 minutes. And then after the 15 minutes, it would just freeze up and not let you edit anymore, and you'd be forced to click the submit button. That's what's supposed to happen in the exam. All right, on to the time basis of signals. So what are the different bases we can use for signals? So here we have a statement where, if you recall from the end of lecture set 3, I made this bold claim that any signal is a series of scaled and shifted delta functions. There's uncountably many of them, filling up the entire domain of the signal, and they each have an area. Delta function has an area given by that function value at that point. So, we say x of t is, the statement of the shifting property, which is the limit as delta t goes to 0 in a sum from k equals minus infinity to infinity, x of k delta t times delta of t minus k delta t. So we're kind of going from a continuous version of this to, this, Riemann sum approach, where if we ignore the limit part, we have a discrete function now. And so we have this discrete basis representation of x of t at times t sub k. So we'll have x at t sub k minus 1, x at t sub k, x at t sub k plus 1, and so on and so forth. So we can represent a given point in time as an amplitude times unit vector. So we'll say x of t sub k is x of t sub k, and then a bunch of zeros, a 1 in the middle, and then a bunch of zeros. And, that's, that function at that time instance. And we can add up several such functions with, different unit vectors here. And we would get the entire function back. So, probably easier to think about a function with finite support before you deal with an infinitely long function. But, we're basically claiming that, when you have a, time domain function, this is what we are doing. And then these unit vectors, the 0, 0, 1 in one place, and then zeros everywhere else, span our Rn space. That's the vector space Rn. If you haven't had linear algebra yet, you might be a little confused. Don't worry about this too much. We're just trying to, say, okay, if we have this discrete signal, we can represent it, cleanly and without overlap by, these types of vectors times function values. So cleanly without overlap is the informal way of saying orthogonal, which is there is a dot product of 0 between any pair of these unit vectors. Thus, they form a basis set. So the next way of thinking about signals besides a time basis would be a frequency basis. So this would be using sines and cosines of various frequencies to represent a signal. So we can say any signal is just a sum of sines and cosines of various frequencies, including the 0 frequency, which is, cosine of 0 being equal to 1. So that's the constant component, the DC component of a signal. So these are the phasors studied in ECE 20001. That's a typo, studied, past tense. The inner product of two sinusoids over one period is 0 whenever omega 1 is not equal to omega 2, meaning they are orthogonal. And if you wanted proof of that, I forgot to put it in slides, but basically something like this, where we take 1 over t, integral from t to t plus capital T, sine of omega tau 1, or omega 1 times tau, times sine of omega 2 times tau, d tau. If you perform that integral, you will always get 0 whenever you have omega 1 and not equal to omega 2. Your book goes into a little bit more detail of a proof. But when omega 1 equals omega 2, suddenly you get a non-zero value. So I'm claiming that, sines and cosines are sinusoids of different frequencies are orthogonal to each other. So that means we have a basis set formed by sines and cosines of various frequencies. So if you expand your view of this basis set into the complex world and you use e to the j omega t, a complex exponential, this basically becomes the Fourier transform in ECE 301. Notice I said Fourier transform. It looks like Fourier, but that's not how you pronounce that word. So Fourier. And you'll have all of ECE 301 to look forward to the Fourier transform. So the Fourier transforms only solve for steady state solutions, leaving out the transient response we have studied so far. So by transient, we mean the part that decays away. Fourier transforms will only get you the steady state solution, which would be constant steps and sinusoids. So we're going to move from, the frequency basis all the way up to a complex exponential basis of signals. So ECE 20002 requires a superset method of the Fourier transform called the one-sided Laplace transform. So I have a friend who claims that he understands Laplace transforms but doesn't understand Fourier transforms. That shouldn't be possible, because if you understand Laplace transforms, you can get the Fourier transform for free by doing one simple trick. So we're doing with something that's even more powerful than the Fourier transform you'll study in ECE 301. So the basis set here are complex exponentials e to the st, where s is a complex number. So complex exponentials cover the gamut of responses we've seen, sinusoids, exponential growth decay, steps, as exponentially decaying or growing sinusoids as well. All of those are included. The downside is that arithmetic will be with complex numbers. So s is part of the complex numbers, such that s is equal to sigma plus j omega, where sigma is the real part and omega is the imaginary part. And remember, we're electrical engineers, so we use j for the imaginary number. So j squared is -1. I is sacred, I is for current. Sounds positively joyous. Well, it's not just positive, it's also all the complex numbers. So it's complexly joyous. So the Laplace transform, named for Pierre-Simon Laplace, a French mathematician, which I don't have written down. Integral in helping figure out the Laplace transform. And I say that as a pun because it takes a signal from the time domain to the complex frequency domain. S equals sigma plus j omega. So we get rid of the time variable t and we go to complex frequency s. We denote the Laplace transform as capital X of s equals script L. When I handwrite this, I just use my normal cursive capital L, and then in curly braces x of t. So the Laplace transform of time domain signal x is defined as the integral from t equals 0 minus up to infinity of x of t times e to the negative st dt. Get very comfortable with this integral definition of the Laplace transform. We use it a lot. You're expected to know how to do this. And it's not too hard. So if you ever ask, what is the Laplace transform? You could say it's this integral transform where we, get rid of the time variable t and replace it with a complex frequency variable s through this integral. So we use a one-sided Laplace transform for t greater than or equal to 0 because we primarily work with causal signals, the ones that, suddenly become non-zero in response to a cause. And we want to avoid further aggravation in our lives. Why make things any harder? ECE 20002 is a difficult course. The two-sided Laplace transform is difficult. One-sided Laplace transform, good enough. We think of capital X of s as taking a complex valued input of real and imaginary parts, because S is real and imaginary, and it produces a complex valued output. In polar form, we normally think of it as magnitude and phase. So the magnitude exists in the open interval 0 to infinity, and the phase is in the range, negative pi radians inclusive to positive pi radians not inclusive. So, 360 degrees, from minus 180 degrees to 180 degrees, if you prefer to think in degrees. So here is a diagram that you can find in your textbook in a lot of different places about how we solve problems with Laplace transforms. So at the top parts are our time domain bits. The bottom parts are our frequency domain bits. So before, what we were doing was a direct left to right along the top. We took a function x of t. We had put it into an LTI system with frequency response h of t. And then we said the output was y of t is equal to x of t convolved with h of t. What we're going to do now is take a more roundabout path, but by being more roundabout, it's also easier to do than a convolution. So we'll take x of t, we'll take its Laplace transform, x of s, and then we'll put it through an LTI system with frequency domain impulse response, h of s, and then we'll say y of s is equal to x of s times h of s, and then we'll get y of s and inverse Laplace transform it to get y of t. Where to get from h of t to h of s, there is a Laplace transform involved as well, but that one was already done for us, hopefully. So this is the flow: x of t to capital X of s through h of s to y of s, and then down to y of t. And to give away sort of the big thing we're going to talk about 2 lectures from now, we have replaced convolution, y of t is x of t convolved with h of t, with multiplication with complex numbers. Y of s is equal to x of s times h of s. So that is, a huge advantage, is the calculus is going to disappear as long as we, the calculus disappears along the bottom track. There's calculus involved with the Laplace transform and the inverse Laplace transform, but, the idea is hopefully make it go away in some ways so that it's out of sight and out of mind. So one last thing in the sort of motivation of the Laplace transform. So recall that e to the negative st has s equal to sigma plus j omega. You'll get tired of hearing me say that, but that's the truth. E to the negative quantity sigma plus j omega times t. Oh, excuse me, gotta sneeze. Of properties to break up this exponential into e to the minus sigma t and e to the minus j omega t. We don't need convolution. I mean, you need to know it for the exam, but we're reaching a point in this course where you're not going to see a direct convolution anymore. Thank you. So we're dealing with real time domain signals. So the output should be purely real in the time domain. So e to the negative st should have the same effect as the complex conjugate of e to the negative st, which is e to the negative sigma t, e to the positive j omega t. You should have the same effect. So we conclude that outputs in quadrants 1 and 4 have the same effect, which is e to the negative sigma t cosine omega t is equal to e to the negative sigma t cosine of negative omega t. And the same goes for quadrants 2 and 3. E to the sigma, or e to the plus sigma t cosine omega t is equal to e to the plus sigma t cosine of minus omega t. Remember, cosine has this even function property, or if you take cosine of a negative argument, it's equal to just cosine of the positive argument. No other changes need to be done. So we prefer values in the right half plane. where we have, quadrants 1 and 4, because they're e to the minus segment t. Because these are damp sinusoids that decay over time. We prefer that, Remember, exponential decay is cool, exponential growth is lame in ECE 20002. So as you get farther from the imaginary axis, and you have, sigma values way over here, you have faster exponential decay. And then as you go farther from the real axis, either above or below, that just means you have greater frequency of oscillations. We detest values in the left half plane because the damp sinusoids are going to grow over time. They're going to shoot off to positive infinity or minus infinity. And the farther you are from the imaginary axis, the more so, and with greater frequency when farther from the real axis, whether that's above it or below it. So values dead on the imaginary axis are constant amplitude sinusoids, the phasor realm, which are definitely worth studying. In fact, we did in ECE 20001 as phasors. So we should pay close attention to the region of convergence for the Laplace transform pairs because they dictate where growth or decay can be expected. So we want to make sure we're dealing with areas where we're dealing with exponential decay, not exponential growth. So we'll have to check the region of convergence for our Laplace transform pairs. At least for this lecture set. After a while, we just assume we're dealing with signals such that, we're in, usually in quadrant 1 or quadrant 4. What questions do we have? Again, if you're confused about what the Laplace transform actually is, go back to slide 7, put a star on it, and say, okay, we really need to know that boxed equation because it defines what the Laplace transform is, and it, reminds us that we use capital letters. We use capital letters to denote the, the function as well as the s variable. This integral defines what the Laplace transform is, so hopefully we're not confused about it. We're until we see the properties, we're going to question why we're going to do this, what's the utility, but we claim that this is the fastest way to solve circuits. That L is so beautiful. For those who love tech, it is written as follows. It's called MathCal for calligraphic. Yeah, I don't know. As a random aside, who would be interested in a LaTeX workshop? Do people want to learn LaTeX? Okay. I might have to do it on a weekend, but I'd definitely be willing to hold one of those. It's useful. How to do a circuits. What is LaTeX? It is it's not a markup language. It is I guess it is a formatting language used to make pretty math documents. All of my slides have been made with LaTeX. There is no PowerPoint document. This is all made with LaTeX. It's LATEX. Usually with weird capitalization and up and down, but latex. People say it's that way. Could be interesting. Okay. So let's apply the Laplace transform to the derivative. So already we're going to just get a Laplace transform property. So if we take the Laplace transform of the derivative of a function, that is going to be the integral from 0 minus to infinity of d dt of f of t e to the negative st. And then I did another typo here. Recall that we use capital letters to denote the Laplace transform of a function. F of s is equal to the Laplace transform of f of t. Now we do use capital letters for the Fourier transform as well, but I'm meant to talk about the Laplace transform here. So f of s, capital F of s, is the Laplace transform of f of t. So we can use integration by parts to find the Laplace transform of derivative. So recall, integral of u dv is equal to evaluation of uv minus the integral of v du. So we want to integrate the d dt, so we'll set that equal to our dv. We'll have u be e to the negative st, so we'll get Laplace transform is equal to this, f of t e to the negative st from t equals 0 minus to infinity plus s integral from 0 minus to infinity of f of t e to the negative st. So we plug things in. At t goes to infinity, we'll just assume that, this is an exponential decay. So we'll just assume that it beats out anything that f of t is doing. So we'll claim it goes to 0. And then at t equals 0, well, remember, e to the 0 is 1. So we'll get a minus f at times 0 minus. And then we'll have plus s times, this looks just like our Laplace transform definition. So s times capital F of s. So I talked about that assumption we made. So that's equivalent to saying, if this is an exponential decay, that means that the real part of s has to be greater than 0. It exists in the right half plane. So we get the following at the bottom of our page. The Laplace transform of the time derivative of a signal is equal to s times its Laplace transform minus the initial condition at time 0 minus, with the region of convergence, that's Rlc, being the real part of s greater than 0. My allergies are really bad today, sorry. What questions do we have? So you could just take this property as gospel, but on your next homework assignment, you will have to derive several such properties. So be prepared for that. And state the region of convergence. So next, Laplace transform of higher order derivatives. So the derivative property of the Laplace transform will chain together. The region of convergence remains the same. So we'll say that the Laplace transform of the second derivative of a signal is equal to s squared times its Laplace transform minus s times its initial condition, then of the function itself, then minus the initial condition of the derivative, the first derivative, with the same region of convergence that the real part of s is greater than 0. And then if we look at, an nth derivative, so I'm using the superscript parentheses n to represent, dn of f of t dt to the n. That's equal to s to the n f of s minus s to the n minus 1, f of 0 minus, minus so on and so forth, to f to the n minus 1 derivative's initial condition. So as you can see, we get this polynomial in s. So here we have s to the n minus 1. And then eventually we'll have quadratic term, linear term, and then constant term. The roots of this, polynomial will help produce the solution. But we're missing a way to go from the final equation in S back to the time domain to what's called the inverse Laplace transform. So right now we don't have any way for any given f of t to know exactly how to get from this last, these two expressions back to our original time domain function. So we'll get to this later, but we'll have to build up some Laplace transform pairs. So a knowledge of Laplace transforms is going to make it faster to solve ODEs using complex algebra approaches. But so what we need to understand is what the Laplace transform does to our basic causal functions we studied before, and also how to get back to the time domain. Otherwise, we're not going to be able to solve any problems unless we look at, how certain functions behave under the Laplace transform And then hopefully when we see something that looks like the Laplace transform of the function, we know how to go backwards using the inverse Laplace transform to get our time domain function. Because recall, we're going to take the Laplace transform of our function, do all of our math, and at the very end take an inverse Laplace transform of our output to get back to a time domain function. We're going to look at these basic causal signals like the impulse, step, and the ramp to get back to time domain, and then also look at exponential decay and cosine and sine. These are the most basic signals that we tend to use. So the Laplace transform integral is linear. It's an integral, so we expect normal integral properties to perform. So we have homogeneity and superposition. So linear combinations are straightforward and easy to solve. So by homogeneity, we mean that if you take a scalar multiple times any of these functions, you get a scalar multiple times the output. But in this case, the scalar multiple times the resulting Laplace transform. And then if you have the sum of two functions, then the Laplace transform of it is just the sum of the Laplace transforms. So now we should be able to work with everything we want. Linearity is almost a fancy way of it behaves the way we expect things, any sort of transformation to behave. So let's look at the unit impulse function. So we have the Laplace transform of the Dirac delta function. Integral from 0 minus to infinity of delta of t times e to negative st dt. That is, their definition of the Laplace transform. However, delta of t is 0 everywhere except at time equals 0, where it is this unknowable thing that goes off to infinity. So, but it's under an integral, so it's well behaved right now. So it's going to be the integral from 0 minus to 0 plus delta t e to the negative st dt. But this is basically only happening at a single instant of time. So we can basically say, okay, it's going to happen at e to the negative s0. Remember, e to the negative s0 is the same as e to the 0, which is 1. So we say that delta of t is the Laplace transform pair of just 1. So we use this bidirectional arrow with calligraphic L above it to represent Laplace transform pair. So on the time domain side, we have delta of t. On the complex frequency domain side, we have 1. Region of conversion, all of s. We don't care. It works for all values. So more math incoming for the rest of today's lecture. So the Laplace transform of the unit step. So what is the Laplace transform of the unit step? Well, it's the integral from 0 minus to infinity of u of t e to the negative st dt by definition. But everywhere on this interval, this just takes a value of 1. So we get the integral from 0 minus to infinity of e to the negative st dt. Okay, that's an integral we can perform. We talk about complex frequency and time, but like right now, it's just an integral that is, integral of a function of time, but it just has this, variable s, which is a constant with respect to time. So integrate this, you get negative 1 over s out front, and then e to the negative st remaining. And we must evaluate from t equals 0 minus out to infinity. Well, we'll just rewrite it as the limit st goes to infinity of e to the negative st minus e to the negative 0, which is just 1. However, we'll make an assumption that, this is an exponential decay, not an exponential growth. So as we race time off to infinity, this term will not go to infinity, but instead go to 0. Oh, excuse me. And when that term goes to 0, this is 0 minus 1 times a negative number. So we'll get just 1 over s. So the Laplace transform of u of t is just 1 over s, with a region of convergence that the real part of s is greater than 0, which is what we made this limit work out nicely. I'm going to step away for a second. Excuse me. How do we derive the region of convergence in general? It depends on each problem. So here it was all of S because we didn't have to make any assumption about how e to the negative st behaves. Here we had to make an assumption about how e to the negative st behaves as t goes to infinity. So we want to make it exponential decay. And for that, that means the real part of that has to be, the sigma part has to be greater than 0. Because otherwise it'd be e to the, plus absolute value of sigma t, and that would be exponential growth, which is bad. That's not cool. That's lame. Hopefully that answers your question, AJ. Think if looking at exponents, you can tell if it's going to converge or not. Decay, exponential, yeah. That's an eloquent way to put it, Aubrey. What other questions do we have? Well, this part is a bunch of, math, integral math. At least it's not a convolution math. So we got to do a few more functions to really build up our library of Laplace transform pairs. So what does the Laplace transform of the ramp function look like? So this is integral from 0 minus to infinity, t u of t e to the negative st dt. But the u of t is just a 1, so it's just integral from 0 minus to infinity of t e to the negative st dt. So by integration by parts, we can deal with this, polynomial in t times an exponential. So by integration by parts, we set e to the negative st dt to dv, and then we set u is equal to t. Then we plug in our integration by parts formula. We get something that looks like this. So the valuation negative t over s e to the negative st, evaluated from t equals 0 minus to infinity, plus the integral from 0 minus to infinity of 1 over s e to the negative st dt. So now we need to use L'Hopital's rule in order to evaluate this part right here, because we have improper evaluation here going on. So the part where t goes to 0 isn't too bad because e to the negative s times 0 is just 1, and then we'll have a 0 out front. So that's just 0 times 1, which is 0. That's fine. But we need L'Hopital's to get the first part where t goes off to infinity. So we'll limit as t goes to infinity of t e to the negative st over s. Well, we can move the e to the negative st in the numerator to the denominator and write it as limit as t goes to infinity of t over s times e to the positive st. Then by L'Hopital's rule, the limit as t goes to infinity is the same as we take the derivative of the top over the derivative of the bottom. So that's just the limit as t goes to infinity of 1 over s squared e to the st. But you can just plug in t goes to infinity and you'll get 0. So again, we made an assumption about the region of convergence right there. We said that, as t goes to infinity, e to the st will go to infinity. Or another way of saying that is that e to the minus st goes to 0 as t goes to infinity. So we made an assumption about the region of convergence right there in the step where we evaluated at t is equal to, or t goes to positive infinity. We can just perform this integral right up. So, this, this becomes 1 over s squared e to the negative st evaluated at t equals 0 minus to infinity. While 0 minus, you just get a 1, so it's just 1 over s squared. And I am missing a minus sign. So this plus sign in both cases should be a minus sign. That is another typo. I apologize for the typos. I do try to check everything, but it's really hard to spot check my own mistakes. I do these slides by myself. So you'll get minus a minus sign to get 1 over s squared. And then again, we make the same assumption that as e goes to infinity, or e to the st, t goes to infinity, that goes to 0. So long story short, the ramp function Laplace transforms to 1 over s squared. We'll see that u of t became 1 over s, delta of t became 1. Hopefully you can kind of see there's a little bit of a pattern going on here. Yeah, Pranav, I think you caught what I just said. I think I think the third line is okay. The fourth line needs a minus sign. Okay. Keeping track of signs. I feel like that's one of the 2 hard parts of this class. Being good at algebra and keeping track of signs. Those are the hard parts of this class. And since we're dealing with complex numbers, you have to deal with complex algebra instead. So let's look at an exponential function. So here we'll have, an assumed exponential decay, e to the negative at u of t. The Laplace transform by definition is this. U of t becomes 1. And then we can use exponent properties to combine this into e to the negative quantity s plus a closed quantity times t dt. Well, this becomes negative 1 over s plus a, and then e to the negative s plus a times t, evaluated from t equals 0 minus up to infinity. Well, we'll take the limit as t goes to infinity of e to the negative. That should be an s plus a as well. Well, technically, it's the same limit. It's technically okay. So I won't change it because obviously infinity plus a constant is still infinity. But I'll make a note that some people might argue about that. So same limit exists here as this limit. And then as t goes to 0 minus, well, it's just a constant times 0. So e to the 0 is just 1. And then minus sign because it's the lower limit of evaluation. So we'll say e to the negative at u of t, Laplace transforms to 1 over s plus a. With a region of convergence that the real part of s has to be greater than the negative of the real part of a. Or, real part of s plus a is greater than 0, if you prefer to write it that way. The real part is just a linear function itself.
I have a quick question about that problem.
Yeah, Aubrey, go for it.
So you're taking the integral, right? And then you have like e to the negative s plus a from t equals 0 minus to infinity. And then you go to taking the limit. I don't understand how you go from that like integral to a limit.
Okay, so in calculus 2, whenever you deal with infinity, you're technically not plugging in infinity, you're dealing with a limit, right? It's called an improper integral. So you would just say, okay, the limit as t goes to infinity of e to the negative quantity s plus a t would be the first term. And then you can take the lower limit, no problem. Do we agree on that bit?
Yeah.
Okay. So I guess what part is troublesome for you?
I suppose it's that, like, I think of like an integral as like the area under the curve, whereas a limit is like the value that a function kind of converges on as time goes to infinity.
Okay. Right. So, but you can also take limiting behavior, which is like, as time goes to infinity here. So it's not just converging to a value. Infinity is a very special value. That's not
Right.
really a value. And remember, this is after we've taken the integral technically.
Okay.
So this is just trying to figure out what the value is, or what value we should get for the first part of our evaluation.
Okay.
Because
Yeah.
the integral's gone by this point. We're just trying to evaluate.
I got you. Okay, that makes more sense.
Okay. I try to show all my steps, but sometimes I forget, things like that where I'm like, okay, we're technically replacing the upper limit with an evaluation, or the upper evaluation with a limit, I should say. What other questions do we have? In the interest of time, I'll press forward with the last two slides and then check back for questions. So here we have the Laplace transform of cosine of omega naught t, u of t. Well, we need a fancy way to write cosine with complex exponentials. This is the way to do it right here. It's this top part over 2. It's e to the plus j omega naught t plus e to the negative j omega naught t all over 2. That is the complex exponential definition of cosine. It comes from Euler's identity. You can figure it out if you look at, e to the, plus j omega naught t and e to the minus j omega naught t, add them together and then divide by 2. You'll get that. You just get the cosine bit of, cosine omega naught t plus j times sine of omega naught t. If anyone has questions about that, I could show that in a Piazza post or something. So we can factor the 1/2 out front, and then we'll get an e to the minus quantity s plus j omega, and then e to the minus quantity s minus j omega. So when we do that, we will, do exactly the same trick as we did for the Laplace transform of the exponential. We're going to get 1 over s plus a. So we'll get 1 over s, and then in this case, a is minus j omega naught. And then here, a is equal to plus j omega naught. But this isn't very fun. We've got a sort of mismatch of, a complex number with an imaginary part, and then it's being added together. We can simplify this down a bit by getting a common denominator. So we'll get, multiply through by s plus j omega naught, this term, second term by s minus j omega naught. And then lo and behold, the j omega naughts cancel in the numerator. And we can evaluate the denominator as s squared plus omega naught squared as a sort of, complex difference of squares. Then we get 1/2 2s over s squared plus omega naught squared. I claim to you that cosine of omega naught t, u of t, is Laplace transforms to s over s squared plus omega naught squared with a region of convergence such that the real part of s is greater than 0. Because we use the trick here for evaluating an exponential, the real part of this is just 0. So we'll say real part of s is greater than the negative real part of 0, which is just 0. So that's where this region of convergence comes from. It comes from applying the exponential function Laplace transform that we just derived. So we get s over s squared plus omega naught squared. Sine gives us something very similar. We'll get omega naught over s squared plus omega naught squared. This is the definition of sine. It's e to the plus j omega naught t minus e to the negative j omega naught t over 2j. So we get this minus 1 over j2 out front. Now the s's cancel instead of the j omega naughts. So this is the sort of thing we get out at the end. What questions do we have? Hearing no questions, I want to remind you, homework is now due tomorrow. Please do not procrastinate it. Please still work on it today. But I expect to see a lot of you in office hours. That ends lecture today. Let me know if you have questions. You're welcome, everyone. Goodbye.